I work on an application called Wunderlist. I talked about that yesterday. In a nutshell, this is what it is. It is a to-do list application. So if you go onto Google and search for to-do list or build a to-do list application, you will find something like 228 million results. So I can say that the to-do list is basically the new hello world of applications, and this is what I've dedicated myself to doing. I moved to Berlin 2.5 years ago to work on this, and previously I was SVP of technology for Living Social, which was doing massive scale. We were setting like e-commerce daily world records, and I had an international 350-ish person team that was working for me, and I left to go work on a to-do list. So everyone was like, why are you working on a to-do list? That's so strange. Well, there are a lot of good reasons for it, but I do want to explain a little bit more about what I mean by to-do list. It is simple. You can download it. It's free. You can put it on any device you have. It's cross-platform. We have actually built it in a way that it feels very simple, but you could use it for full collaborative real-time project management. And if that doesn't impress my technical friends, then I will call it sometimes a cross-platform, multi-user, multi-master distributed, mobile-friendly database replication system. With a to-do list front end. I can't repeat that. No, never again. That's the last time. And it's actually a lie because it's not exactly multi-master, but it does work offline, and you can edit offline, and then you can sync things together. And building a thing like this is actually pretty difficult, it turns out. And the team that built it before me, I didn't build the initial version, they learned how difficult it was a few times. So they had Wunderlist 1 initially, which was written like a startup. You know, it was basically an MVP. The sync was really weird. It was this PHP backend. It was never going to work. They knew that, but they got some popularity. It was the right thing to do. Then they were very proud to launch Wunderlist 2. Now this was launched before I joined, but after I signed the contract. So I was already like in the team hip chat talking to the people, and they were very nervous. And I like to say that my marketing team is pound for pound the best marketing team in the world. So it's very small, but very, very effective. So when they launched Wunderlist 2, it was featured globally on all the app stores, and everyone was talking about it. All the press were talking about it. And that was really good in some ways. Of course, you want that when you launch your app. Does anyone use New Relic in the room? Okay, so New Relic is a monitoring tool for performance management especially. This is actually a screenshot that the CEO took right after the launch of Wunderlist 2, so he could start spamming everyone in Germany who was a back-end developer to say, can you help me? Because the back-end caught fire, and basically the entire application was down for 48 hours straight. So on this massive launch that they had been working for months to do, it was a total rewrite of the system, top to bottom. They were so proud of it, then they launched it down 48 hours straight. Imagine, like you've probably worked on outages before if you work on any back-end systems, it's very stressful. 48 hours nonstop, completely down, couldn't do anything. But then there were actually like an entire week where it barely worked, and then 2 months where it was just limping along. So it was a really, really, really rough experience, which actually sets the stage for when I joined. So I moved from Washington, D.C. to Berlin, like I said, 2.5 years ago. It was 2 months after the launch of Wunderlist 3, almost 2 months after the launch. And Wunderlist 2, sorry. And what I encountered was they had built for the back end, and we're mostly going to talk about the back end today, they had built one monolithic application. It was a Rails application. It was a set of REST endpoints primarily. And on top, application was sitting on top of one monolithic Postgres database that they were managing. So one big blob of code and one big blob of database and millions of active users. It wasn't going to work. There were too many hotspots. In the back end, they had one language. It was all Ruby because it was a Rails application. The entire team was just completely Ruby focused, Ruby evangelists, and in fact, they hired me thinking that I was coming because I was a Ruby expert. And I was pretty good at Ruby, but you'll find out that we did very little Ruby after I joined. In fact, it was like a month in, I suggested doing something in Scala, like because I thought there was a a situation where it would make sense, and people literally laughed, like they thought I was joking when I suggested using a language other than Ruby. We had a test suite for the monolithic application that took forever to run, and I think it was like 10 minutes, or I don't know, because really once it's more than a minute, it's completely useless. You might as well throw it away. Tests that take forever to run, you don't run them. They become a liability. You spend more time fixing the tests than you do working on the code. It's terrible. You have breakages, and you see we had this nice plugin where green would be a nice green heart, and red would be a broken red heart. So anyway, that's what that was. So the test suite was pretty useless. Now on the day of the launch, I was on HipChat, and of course it crashed, right? And a lot of it was database backend stuff. So I said, have you done anything with caching at all? And they said, no, and then they furiously typed in a bunch of code so that they could cache things in Redis, which kept them alive, and in fact was the only way they could stay alive after that 48 hours of downtime. But of course, what happens when you cache things? They go stale. And that's like the second of the two hardest problems in computer science or whatever, right? So of course it went stale. Of course we had bugs all over the place when I joined from this caching. And the bugs just kept coming and coming and coming. But the worst thing, this is the worst thing that can happen to any of you, is when I got there, the team was terrified. Like they couldn't change anything. Because deployment, every time they would deploy, it was like, oh God, are we going to be down for 48 hours again? Because it had happened that they deployed, and really just like the blip in the system from the deployment was enough to where the system couldn't handle it and they could never correct and get back. So the team was terrified. They wouldn't do anything at all. They had built this thing. They had built actually something very complicated because, like I said, it's just a to-do app, but it also has all these different collaboration features built in. So there was a lot of logic. And because it was all built in Ruby and one language and one monolithic thing, you know, of course they didn't want to have a bunch of duplication. They didn't want a big, ugly monolith. So instead they created this beautiful layered set of abstractions. And the net result was at the end, you couldn't find where anything was because there were all these Ruby modules mixed in all over the place and metaprogrammed. And this is a pattern that I see a lot. I heard a talk at Nordic Ruby a couple of years ago by Reginald Braithwaite where he said, Ruby makes the most beautiful coupling, which is actually true because you can do anything in Ruby. It's just this dynamic language. You know, there's no rules. So when I joined, back to this fear thing, the first thing I did, I think it was the second day that I was there, I actually sat down, I had gotten all the access to the system, and I logged in, and the first thing I did is I started removing resources from the system, just one at a time, like one less server, one less server, one less server, and eventually it crashed. And the whole backend team was looking at me like, what the hell are you doing? I thought you're the new CTO, and you've just come here and you've crashed the system. Why did we hire this guy? He was supposed to help us. And then we spent maybe a couple of hours like desperately firefighting to bring it back. And the next day, me and another developer, we did it again. And we did that every day for a while, just for a few weeks. And then we tweaked things. And what we did is we started to find the boundaries of the system. But most importantly, the first thing that we had to do was eradicate the fear of a system that failed by just forcing it to fail. Because I believe that fear that is oppressing a team is really the worst thing, and you can't make any progress until you erase it. So I had come into this company with a fairly strong point of view about a specific set of problems facing the industry. This is actually the title slide from a keynote that I gave at Scala Days last year, I think, where the title of the keynote was Legacy. And I have spent a lot of time over the last several years exploring the word legacy and how it applies to our industry. But you notice that I put my title as Systems Euthanizer. Now, I know we're speaking English as a second language here if we're lucky, so euthanize means to kill something out of mercy. So like when someone is sick, you kill them so they don't have to suffer anymore. That's what euthanization means. So I put my title here as Systems Euthanizer because I have been fortunate and unfortunate in certain ways to work on project after project after project in my career where I do a large rewrite of a system. And what this really means is I take an existing system that someone like me has spent like a year or months or whatever, years pouring their hearts and souls into, doing late nights and stress and all these things that you feel when you're developing software, and throw it away. It's just gone. And I hate that. And I even wrote a series of articles in 2006, 9 years ago, called The Big Rewrite, lamenting this, complaining that I keep having to do this, and talking about how to avoid doing big rewrites. And so I started thinking a lot about the word legacy. And in our industry, we use legacy in this way. We use it as a negative term. Did I just turn off my screen somehow? I wonder what I did. Oh, it's back. Weird. I think it's a keynote bug. The quality of Apple products it's great, actually. It's really great. I work for Microsoft. So we use the word legacy as a negative thing, right? Like, probably no one in this room says, I'm going to go search for jobs online. I'm going to type legacy and then .net or whatever, and that's how I'm going to find my job. But as I said yesterday, I come from the music industry, and in the rest of the world, really, the word legacy means something good. It means something that you leave behind for future generations. In a good way. So like a birthright, the legacy of an inheritance that your family leaves to you, or the teachings that your parent give you that pass on like their way of thinking and their morals and their ethics to you. Legacy is actually a good thing. So like a composer, as one example, Beethoven, he left a legacy. He left a legacy so great that even an American can pronounce his name. We know who he is. I can hum his symphonies to you, and you can probably hum them to me. We should do it. It would be terrible. But here's the problem. So in our industry, this is like a really inexact view of the Standish Chaos Report. And the Standish Chaos Report is a report that is gathered by a group called the Standish Group, annually, I think, where they go survey a bunch of different companies and projects, and they give some idea of how well we as an industry are creating software. So I don't have the exact numbers on here, it doesn't really matter, and it stops at 2009, but if you keep going, it looks exactly like this, because it hasn't really changed over the years. Basically, we have the green bars, which is the bottom bars, in case you can't see color, are successful projects. The red at the top are failed projects, so we know what that means. And then the silver gray part in the middle are challenged. And in the Standish terminology, challenged means significantly over time or over budget or both. So to me, that's sort of a failure too, which means just this bottom little band here, this is us doing successful projects as an industry. We really suck. We really do. I said in my keynote the other day, most people suck at their jobs. Here's the effect. And for business software that actually makes it to production, on average, within about 5 years, I come and throw it away. And I made that 5-year number up, but it sort of matches my experience in the industry. So if you can get something into production, into the market, it probably doesn't stand a great chance of living for a long time. Probably Standish should do a report on that too. So then you have Joel Spolsky, several years ago wrote this thing about how it takes 10 years to create good software. So if software generally doesn't get delivered, and when it does, it's probably killed within 5 years, but certainly within 10 years on average, and it takes 10 years to even make it good, we have a serious problem, right? We're not going to leave a positive legacy of our work. And in fact, the work that we do, most of the work that all of us in this room do, will be absolutely forgotten even by the time we retire. And none of it will have ever actually mattered. So that was the uplifting part of the talk. So I started wondering, how do you create legacy software? Because we shouldn't talk about legacy software as it's a bad thing. Legacy software is something that actually existed long enough to where you could call it that. That's a pretty good thing to aim for. Software that was useful for a long time. How do you do that? And I asked my friend Mike Feathers, who wrote the book Working Effectively with Legacy Code, which you should read after you finish The Pragmatic Programmer. And he pointed me to an excellent paper by a man named Richard Gabriel, who is, I believe, the first person to ever write about patterns in software. And he is something like a technical fellow or one of those fancy titles at IBM where he just does research and thinks big now. He also created the common Lisp object system. He's a very impressive and underrated person in the industry. Anyway, he wrote this thing which is called Designing Beyond Human Capability. And it's a paper about creating a system that's larger than any human could ever actually think about, just as an exercise in thinking about how to deal with very large problem sets. And he talks about how biological systems are larger than anything coherent we could ever have created. So like the human body, for example, is a system, right? And that system is more complicated than any software system that any set of humans has ever created. And there are a bunch of interesting things in here that inspire a whole direction in thinking. For example, the way that biological systems can survive. Like, I am 41 years old, and I don't deserve to have lived longer than a software system, because I have not been maintaining this system very well, I can promise you. So it's a miracle that I'm 41 and I'm standing here talking to you right now. So there must be something right about biological systems. So he says, when a cell is not healthy, an outside cell that's part of the immune system can command the cell to destroy itself without spreading toxins. This is one of the key parts of how biological systems can survive. And we've all heard it all our lives, and there's some truth to it, but like the me that's standing here today is made up of entirely different cells. That's not actually 100% true, but entirely different cells than me at 5 years old. So that's an important part of how I can survive. The system survives. The components of the system don't survive. And then the biological systems also support a thing called homeostasis, which is a process of balancing things out. So it's like this regulatory process across the entire system. So what if we took this idea and applied it to software? So like what I want to avoid ever doing is having a big rewrite where I've got this one massive system that doesn't work, or it doesn't work like I want to, or it's too expensive or whatever, and I want to spend a year trying to rewrite it in this risky, terrible project to deploy it with a new technology. I want to avoid ever doing that again. How do we do that? Well, I think if we can think about systems and cells properly, we could take this idea of cellular regeneration and rewrite the system slowly and constantly. And that's sort of the idea that we apply at Wunderlist. So we have to think then, what is a cell in a software system? And then what is the system itself, or which pieces are maybe subsystems? And when you're thinking about software architecture, which one do you write? Like, do you need to be writing a cell right now, which should be regenerated, or do you need to be writing a system, which is a larger kind of mass of things? So anyway, back to reality and out of the theoretical realm. And I apologize, I am really feeling jet lag right now, and maybe I'm going to say sentences backwards and stuff like that, so just laugh at me when it happens and point. So back to reality, we're at Wunderlist. I'm attending the board meetings. We basically figure out after 9 months of me being there that there is no way that we're going to be able to gradually get this system into good shape. It's too tightly coupled. It's just bad. It's not a good architecture. And I really didn't want to do that. I did not want to come and do yet another big rewrite, and that's not what I had signed up to do. So we went to the board meeting, and when one of the investors found out that we were doing a rewrite, you could just like hear the tension in his voice. He was on the phone, thank God, and not in person. But you could almost like see the red of his face through the phone line. And he said, please tell me that if you do this, I'm never going to hear you have to say to do this again, ever. And it was really like, we're pulling the money, it's terrible. And so I spoke up and I said, okay, if you ever hear that we have to rewrite this system, we have to do a big rewrite again, you can fire me and you can publicly shame me, and I promise I'm going to leave the entire software development industry. And he said, okay. He felt much better. So this obviously is what we built. And that's the end. Any questions? No. Woo! Whee! Thank you. Fortunately, I drank most of this before we started. But there is enough that I can slip and hurt myself, so that'll be funny. Okay. So this actually is what the architecture looks like. I'm not going to go through it here, but this is slide number 30. Help me remember that, because I might come back to it at some point. That's why it's here. But you get an idea. There are a bunch of different subcomponents of the system. And so like you have computers and mobile phones, of course, talking to it. Then we have this real-time proxy thing that I'll talk about, and then a smart HTTP proxy, and then a couple of layers of lots and lots of little services. And why did we make little services? Because we wanted to start thinking about things in terms of cells, right? So I made a few rules, and it wasn't really rules, it was more like ideas that we spread through the team as we started working on the new architecture. The first one is that services in general should be about this big. And the reason I wanted them to be about this big and no bigger than this, and literally I mean like, you hold your fingers up on the screen and the whole thing fits in this much space, is that anyone can understand anything you do unless you're really trying hard if it's no bigger than this. And that was very different from the system we had before. As I said, you couldn't find where logic was. It was all in these crazy abstractions. So we would do stupid things sometimes, but it would just be this big. I also let developers choose anything they want about the tech stack. Each and every developer has complete flexibility to make choices as long as they follow a set of rules, and one of them is it must be this big. We have this multi-tiered architecture, which is a little bit strange. And as I mentioned, we have an incoming thing which all clients connect to, which is by WebSocket. It is an Akka Scala service. Every single client that connects gets an actor. And if you don't know the actor model, it would take too long to explain now, but you should Bing it, because I work for Microsoft. The Microsoft guy this morning said, Bing, it's a search engine, you should Google it. I thought that was good. So everyone gets an actor, and the actor is what all requests go through. And so after that layer, everything is just normal HTTP. And I'm just going to show you the picture because it's easier to visualize here. So the smart proxy is not really that smart. It's actually Nginx with Lua. That's one of the languages I often forget that we use. Nginx with Lua extensions that we've written. And then we have two layers under that for REST services. So the first layer we call the English layer. And if you're using an application called like Wunderlist, you have tasks and lists and comments and files. We have services for tasks, lists, comments, files, etc. So there are a bunch of services at that layer. Anything you can think about in the domain of a to-do list would have an English name at that layer. And what these services do is they make sure that you have rights to do the thing that you want to do, and they do any sort of business logic there. So they may have to talk to multiple other services to do that, like to figure out that you have a membership to the list the task is in that you're trying to modify, for example. They never talk to a database. They only make HTTP calls out, which gives them the characteristic that really all they do is a little bit of computation and a lot of HTTP-based I/O, which means that they can scale in a very specific way. And this is important because we are coming from a situation where scaling was of vital importance and very difficult to do. Now the next layer we call the German layer. And the German layer, of course, has like super user access to the database because it's German, and Germans can do anything in our company. So the German layer mirrors the English layer, but for tasks we have Aufgaben, which is the German word for tasks. For lists we have Listen, comments, we have Kommentare, and so on. Now each one of these, like I said, it assumes now that you are authenticated, and it acts basically as a wrapper on top of the database. Each one completely owns its own database. So the tasks, or the Aufgaben service, has complete ownership of the tasks database. The comments or Kommentare service has complete ownership of the comments database, and so on. And as a rule, no service can talk to any database that it is not the owner of. And this is very important for us, because what we have done now is we've created a standardized, convention-driven REST interface to databases, which means we can run any database technology we want. So we currently have Postgres, MySQL, DynamoDB, and Redis as data stores underlying these things. And then we have one more layer that isn't really pictured here, but it's sort of visualized as this blue river type of thing in the bottom. Whenever you do any write operation, so create, update, or delete, a message is pushed, a convention, like a standardized message of the mutation, the change to the object, is pushed into a message queue and then processed by this centralized router that can intelligently figure out who cares about this message. Those are the things that end up getting pushed out to the clients. So when I say real-time, Wunderlist as a client, like if I have my iPhone app and you have your Mac app open or your Windows app open, and I share a list with you, it immediately pops up. You accept it, I immediately see you accept. So it's almost like a remote control. In fact, we still in the office like to just sit and play with it and laugh and giggle when the things are moving on the screens because we're a bunch of children. But so this is what we've built. And the fact that every write goes through the same layer that generates these mutations means we can add pieces to the domain all the time. We could build completely new applications on this synchronization technology, and the real-time messages go from the router both out to the other services for reasons I won't go into too much, but it has to do with maintaining the sync hierarchy, and out to the clients. So each one of these connected actors, which is a long-running process representing the connection of like my cell phone to Wunderlist as my user, has a subscription on the message queue and gets every change. And that's how the real-time thing in the client works. So one of the valuable, if not probably the most valuable thing about having services that are this big, and like I didn't really say microservice yet, and that's by intention because we never meant to make microservices. It wasn't about that. I think like we should all avoid saying that because it's another word that loses its meaning. What we were doing is creating cells that could be thrown away. That's what was important. Because we had a system before that we couldn't change. We needed to be able to change everything all the time if we wanted the system to survive. We don't care if the cells survive, they have to die and go away. So the software itself, as a rule, we are always okay with throwing away software. That is like, not only are we okay, it's sort of a goal that you should continue to throw things away and rewrite them. If you don't like something, throw it away. If you don't understand it, throw it away. If it doesn't run fast enough, throw it away and write it again because it's only this big. You can do it. Not only that, but the way we do deployments is also in this mode of throwing away. So the creation of the software we think of as being like a system of cells, but the actual runtime of the software is also a system of cells. And what this means is whenever you want to upgrade something, you just throw away the old servers that are running it and you replace it with new servers. Obviously not in that order. But so we have a rule that you never upgrade any software, whether it be application software or system software, on an existing running server. Now, of course, we don't have servers because that would be really expensive to throw servers away every day. But we have instances, virtualization. In our case, it's Amazon. It's moving toward containers. That's what we're doing as an optimization layer now. But we throw away the instances. And a beautiful thing about that is you don't have to wonder about the state of those instances. Like, I remember when I was at GE in the 90s, and I had a Sun system. I was telling in my keynote about setting up these Sun systems from scratch. I remember being so proud when we had one that had been running for like a year and a half nonstop uptime. And I was like amazed, And then one day a hard drive crashed, or I can't remember what it was. It was something we couldn't recover from. And we thought, oh crap, we don't know how to rebuild this thing because we don't know what we've done on this thing over time. Now, of course, there are a bunch of different pieces of software that have been created to address this. For example, Chef and Puppet, great pieces of software for 3 or 4 years ago, completely irrelevant in the world of immutable infrastructure, though. And so what we did is we had previously a Chef installation, but when we moved to this world of throwing things away and replacing them, we realized that Chef was just total overkill. And we extracted the stuff from our Chef scripts, and we made simple shell scripts, and then we put some convention around that and threw away Chef, and it was way easier to deal with. So we have a system, you won't be able to see the details of this, it's called Wake. And this gives you some idea. I'll tell you what it says at the top. So at the top I say wake info as files, and this is actually an old version of the command. And it's returning information about all the running servers that are serving the service that is called files for us. And you see there are, I don't know, 9 running. And then you can do stuff like, see what's in the load balancers. We're on AWS right now. Of course, we're moving to Azure because we work at Microsoft. And then you can scale these up, and you can scale them down. So you can say, like, well, I've got this iCal service, which generates feeds for iCal servers, and it's too slow right now, so I'm going to scale it up to 9 servers instead of 3. That's a single command to do that. But we also have this thing that we built, which did not take much time. It's just a stupid Sinatra application in Ruby called awake. And for every repository in GitHub that we have, every time you do a merge to master, it calls back via a webhook to awake and automatically builds a new Amazon image for whatever that application is. So the files service, for example, if I were to create a pull request and someone merged it, immediately in the background it's building an Amazon AMI with everything you need to run that, a golden master. And then I can just click a button and I can replace what's there with my new golden master. I can also move a slider, and I could move from 3 file servers to 100 file servers in a single slide if I wanted to. So you can scale all these pieces independently. And a nice thing about that, going back to my little picture here, is in our current world with all these little services that are independent of each other, if things get slow, it's very, very easy through monitoring to see where the slowdowns are. So you could look at basically a visualization of this map and see, like, oh, the list service is slow, but the listen service is not slow. So what's the problem? It's only in the list service or some other dependency, Whereas in the old world, everything is in this big blob. It's very hard to figure out which pieces in a monolith are actually causing performance problems. You can try, but you have to deal with the fact that you have noisy neighbors in the same process, and it becomes very, very difficult. So in our world, it's very easy now to see where the performance problems are and to scale things up and down independently. Now, this is probably the most radical aspect of our infrastructure. I believe that the root of most of the fear that we have in software development and change is coupling. And so, although I talk a lot about cellular regeneration and being able to throw things away and rebuild them, another important piece of that is that these pieces are not able to talk to each other. And if they do, it's through a very well-defined interface. So we made the decision that we were going to be heterogeneous by default in our infrastructure, which means rather than the normal thing where you say, well, we all know Ruby, so let's invest in Ruby and really make our Ruby infrastructure great, or our .NET infrastructure, or JVM, whatever, we said, no, we explicitly want to avoid that. Because if I have an Erlang process over here and a closure process in the JVM over here, in order to tightly couple those in the way that you can in a single process, you would have to go to very great lengths. Like, it would be difficult to tightly couple them. And so we do have Ruby, Clojure, Go, Scala, Haskell, Lua, Rust, Elixir, Node.js, and probably a few more that I'm forgetting in production right now. Now, how did we decide? I'm making noises. How did we decide on each one of those? Like, what was the technology introduction process? The technology, I'll tell you about Elixir, for example. With Elixir, we had one guy on the team who was not a programmer. He was a marketing intern, and then he joined the support team, and then he decided he wanted to be a programmer, so he learned programming. And then he joined the back-end team. He was a Ruby programmer, and he was really interested in Elixir. And he really wanted to use it. And I said, well, anyone can use any technology they want on the team. All you have to do is fit with our monitoring system, our deployment system, Wake, that I showed a minute ago. The code has to be no bigger than this big. And of course, that can be slightly bigger or slightly smaller, but somewhere around like this. And you have to find at least one other person who agrees that it's a good idea and will work on it with you. So this one guy, who I would say now, he's barely experienced. He doesn't have any college education and he's just taught himself over a few months. He decided not to do it. He had full rights to do it, even though he had no experience. I said, you can do it. He decided not to because he didn't want to go through all that and it felt a bit risky. So then we hired a new person who was just out of college, and she wanted to use Elixir, and within the first week, she followed all the rules and introduced Elixir, and now we have Elixir in our backend because someone right out of college decided they wanted to do it, and it's fine. So that's the way it works. If you're on my team, I don't decide what technology we use. You decide what technology we use, as long as you fit within these constraints. And therefore, I don't know if you've ever been in this situation where your boss decides what you can do and what you can't do, and you're just really kind of sitting around thinking, like, man, I want to use this other technology, and it's a bummer, and you get together at the coffee machine and complain about how you can't do the cool thing because you have to do the old crappy thing because of your work environment. We don't have that. In our world, everyone owns the decisions, and so far it's worked out quite well because we all take ownership and responsibility for the consequences of those decisions. We also decided that instead of having reusable software components that we would share between things, we would have reusable code only in services. So for the most part, that's all we have. The only reusable code we have is wrappers over services. And yes, that makes things slow, but on the whole, what we care about is not the speed of each individual interaction. What we care about is the speed of the system as a whole, and because of all of these other properties, we've been able to achieve much, much better speed than we did with our monoliths. We also took the one big database, and maybe it's because I'm simple and stupid, but I always try to look at hard problems and say, like, I don't like hard problems and I don't want to solve them. I'm not smart enough for that. So I'm going to try and figure out how to take every hard problem and turn it into a bunch of really easy problems and solve those. It's a messy approach, but this is what we've done. So in our case, we took our database and we just completely sharded it up based on the slivers of the domain. And that was actually enough. In some cases, it's ridiculously tiny databases. And sometimes they only have one table. Oftentimes they only have one table because of the way the services have to own the database that they have, literally the entire database. So we have tens of databases with sometimes one table in them. Now there are one or two that are not tiny, but compared to the old database size, they are tiny, and therefore they're very, very easy to deal with performance-wise. And then, as I said, we have many tiny services. So this was a count at one point. I just went through our configuration of all the different things in our deployment system, and we had 151 little bitty services to power this thing, which might sound crazy because it's just a to-do list application, but if you remember that we want components to be shareable as services and not as software components, then it's not really crazy to imagine that a system might have 150 classes, right? This is sort of the equivalent of that, but the classes are accessible via HTTP. That's the way to think about it. And we made this work. Like, it sounds complex, and people often ask me, like, would you really do this for a simple application? Would you do this again? Is this overkill, It isn't really, because the way that we did it is all by convention. So there aren't any crazy big config files that have like all the mappings between things. We just made a convention of how things work, and then literally on the first day we created the new architecture, one other developer and I went to my house and we typed a shell script that looked something like this in my terminal and auto-generated N applications, like literally Rails applications at that time, as you can see, that were exactly the same, but with different names. And that's how we started. So we knew that we had a structure that was exactly the same. We knew the naming conventions were exactly right. We created Git repositories and GitHub all at the same time, separate repositories. And then we built, this is the only shared code really, we built this thing called API client, very generically named, which is the only way you ever talk to a service inside our infrastructure, which means that we have a very standard conventional way of doing all of our HTTP calls, and no one ever has to ask how you do it. Now you see, we have API client, which is the original Ruby one. We have a JavaScript one. We have a couple of ones on the JVM for Scala, etc. We have Elixir, we have Haskell. But every time we introduce a new language, we typically create one of these two, which is a very small thing. As I said, we have this smart proxy. It's really not smart. It's just Nginx, but it has some Lua things that do caching. I won't talk about that too much because I don't have time. And then we have that real-time service, which I already described. So we have been able to do, because of this infrastructure, we've been able to regularly and pretty much always do Canary-style deployments since we created this infrastructure. Are you familiar with that term? It's kind of a nasty term. It comes, I think, from Kentucky in the United States, where in the coal mines, they used to put canaries in bird cages because they're very fragile animals. And if a canary dies, or if all the canaries die, they know they need to run out of the mine because the canary died, but they're about to die too. So it's sort of a sad way to talk about it, but canary deployments means that you're rolling out like a portion of your services are the new version of the service, and you can watch the metrics. And one of our rules is we measure everything for this to work, right? So you can watch the metrics, and if you've done something bad, you can back it out before it's too late, before you screw all your users. So we pretty much always do that. So we have an automated way to see, like, okay, we did 10% and then 50% and then 100% of servers. And before it's too late, we can revert back to the old images, which is, of course, instant. We had to do service resolution because we have all these services. If you want to call the Kommentare service or the Aufgaben service, you have to figure out where to find it. And we did this also really stupidly. The first thing we did is we checked in a YAML file with a list of all the service names and locations. We then converted it to JSON because, of course, YAML sucks, and we already knew that. I don't know why we used YAML. Then we started auto-generating the JSON based on conventions. And then finally, we've moved on to using Console by HashiCorp, which is an open source thing. Really nice. It's worked out very well for us. But all we do with it is generate YAML or JSON files, which we load at start time. So we keep this stuff very, very simple. Message queuing is an important part of our system. So what we wanted to do was feel synchronous with HTTP, but also get the benefits of asynchronicity. So that's why we put in that standardized mutation flow that I was talking about. So anytime you write anything, it goes into a message queue, and then it can be routed anywhere semi-intelligently. And it also routes out to the client. The clients can also issue HTTP requests through this WebSocket thing, and those are parallelized and then put together on, when they come back and sent back to the client. So the client can feel like it's completely asynchronous while the entire chain is synchronous up and down. As I said, we monitor everything, and this is not my fault. This is actually the color scheme on Librado, which we use. But because of how we've done this in AWS, everything's in a load balancer. There's actually one chart that you get for free, which is every load balancer's latency. And it's amazing, just from having this and all these services, this is almost all we ever have to use to figure out where performance problems are when they pop up. Because you just mouse over and you see, oh, it's these two services are slow, and you know exactly where the problem is. So it's pretty amazing. I will skip the details of how we migrated. You should look this up if you get a chance. It's called Saving Our Bacon with Evil Cucumbers, so it should be very easy to search for on the internet. But we did a pretty crazy thing with testing before we launched this thing because it had to work, and basically simulated a bunch of crazy clients. So search for that. Wrapping it up here, I've got 20 seconds, but I'm going to go over, even though I shouldn't, and you can just boo me off the stage. But I have 10 seconds left. See? God, I'm so stupid. We launched this thing, and it had the same fanfare as before. And one of our lead investors told me, no pressure, man, but If it's up in 1 second after the announcement, you'll know that you did okay. Because last time it was literally 1 second and the entire thing was down. That's all it took. So huge stressful situation. We had like a mission control, but we launched it and we thought like, was our marketing a failure? What happened? Because we didn't see a blip. The only blip was there was this huge spike on one service and I was like, oh no, and I went and looked at it and it was our Haskell service, which had spiked from 2 milliseconds to 7 milliseconds as an average response time. And I was like, oh, okay. Got to rewrite that then in assembler or something. So I told our investor that we were never going to do a big rewrite again, right? I lied, sort of, but not really, because we launched this thing in August of last year, and at this point, I said we have 150 or so services. Literally, almost none of them exist in the form they used to be. We replaced almost all the Ruby with Scala, Clojure, Haskell, etc. And every time we did that, we would be able to do something like take 30 Amazon servers and turn it into 3, because we were able to rewrite a component in a language and virtual machine that could deal with concurrency better. So we saved hundreds of thousands of dollars, and no one ever noticed that we were doing this. There was no project to rewrite the thing. And we're constantly replacing these things all the time. We had to upgrade Ruby versions in a significant way. There was no project where we were afraid. We just try on a simple one first that we're not too worried about, deploy it, it's okay, then we do a more important one, et cetera, et cetera. I think this thing is working. So I'm not trying to sell you microservices or any of this crap that you hear about on the internet now, or even immutable infrastructure, which is a term that I even coined to describe this. But I do want to tell you this story. The story of coming from a situation where you have this like static system that you're terrified of to a system that can scale and can progress forward and can give you as developers flexibility and fun and freedom to experiment and play and all the stuff you like in your job. And people call that microservice architecture, I guess. I read this funny tweet a while back, which was, I'll share these slides, so the rest of this really, there's always like 3 or 4 slides I should have deleted anyway. Those were them. Francesco Cesarini, who is a well-known Erlang guy, he tweeted this from CraftConf earlier this year, actually. As we get more and more sophisticated microservice implementations, each one grows their own crappy version of Erlang. Any Erlang programmers here? One. So everyone should go talk to that guy after this, because Francesco is right, actually. We have grown our own crappy version of Erlang. And I think the next step for us is to figure out that all these architectural things that we call microservices and immutable infrastructure today were actually invented a long time ago and perfected even in systems like Erlang. So maybe the next step for us is to refactor to a monolith and try to get the benefits of the microservice architecture. Thank you very much.